A storm is forming in water that should not be this warm, not at the surface, not hundreds of feet below it, and satellites are picking up a signal forecasters have been dreading for years. In the next 24 hours, a system that barely qualifies as a tropical storm can become a monster strong enough to flatten a coastline. We have seen it happen. We are about to see it happen again. Stay with me. You will learn why warm oceans are now storing heat in layers scientists did not expect, why one hidden current can turn a normal storm into a record breaker, and why the forecasts you trust may only give you hours, not days. If this pulls you in, hit subscribe. We're going deep. Prepare yourselves. The real threat is not the wind. Satellites spotted it before anyone on land did. A patch of ocean, wide and quiet, holding more heat than it should hold in this season, at this depth, in this part of the world. No storm had formed yet, no clouds had gathered, but the fuel was already loaded. This is how the new age of typhoons begins, not with wind, with warm water sitting still. For decades, forecasters watched the surface. Sea surface temperature was the headline number. Cross a certain threshold, add moist air, subtract wind shear, and a tropical storm could be born. That rulebook still works. It is just no longer enough, because the heat has gone deep. The National Oceanic and Atmospheric Administration, along with research teams across Asia and North America, now track something called ocean heat content. Think of it as a heat bank account, measured not just at the top of the water, but hundreds of feet down. When that bank account is full, a storm passing overhead finds fuel everywhere it reaches. When it is overflowing, a storm can double in strength in less than a day. That is what forecasters are watching right now. Not a specific storm, the conditions that make monsters. In 2025, the Japan Meteorological Agency logged 27 named typhoons, the highest number in 6 years. Many of them intensified faster than models predicted. Some changed course in ways that defied the standard playbook. A few brought rain bands and tornadoes that appeared almost without warning. Entire towns in Taiwan, Japan, and the Philippines learned the same lesson within weeks of each other. The forecast window is shrinking. That is the real concern. Not that storms are coming. That the warning time before each one is collapsing. A private forecaster named Alex De Silva, speaking about the upcoming season, said his team is very concerned about rapid intensification. He pointed to water that is exceptionally warm, and warm hundreds of feet deep across most of the basin. That single detail, hundreds of feet deep, is the piece of the puzzle most people miss. Surface heat can be stirred away by a passing storm. Deep heat cannot. Picture it this way. An old storm moving over warm surface water was like a fire burning through a thin layer of gasoline. It would flare up, then run out. A modern storm moving over deep warm water is like a fire floating on an ocean of gasoline. It keeps pulling more fuel the longer it stays. The self-limiter that used to slow these systems has been quietly broken. And the pattern is not limited to one ocean. The same deep, warm layers are being measured in the Western Pacific, the Caribbean, and the Gulf of Mexico. 3 different basins, 3 different coastlines, one shared ingredient. So when you hear a forecaster say a typhoon is strengthening faster than expected, that phrase is carrying a lot of weight. It usually means the storm has found one of these reservoirs. It usually means the next 24 hours will not look like the last. The water is the real story. The wind is just what the water becomes. And the next layer of this puzzle, the one that turns a warm ocean into an unstoppable engine, begins with a single physical rule most people have never heard. A rule that used to protect coastlines, a rule that is now breaking down. For most of the 20th century, a tropical storm had a built-in brake, a self-limiter nature included, almost like a safety switch. When a cyclone moved over warm water, it also churned that water violently, mixing the surface with cooler layers below. Within hours, the storm was sitting over its own cooled path. Its fuel supply dropped, its winds eased, the coast exhaled. This rule saved lives, quietly, invisibly for generations. The mechanism is simple. A hurricane or typhoon is a heat engine. It lifts warm, moist air up from the ocean surface and rotates it into towering thunderstorms. That rising air is what powers the wind. Strip away the warmth underneath, and the whole engine starts to starve. Forecasters counted on this. Coastal communities counted on it. Even when a storm looked terrifying on satellite, there was an expectation that it would peak, then weaken, then fade. That expectation is now unreliable. Because the brake depended on one thing: cold water waiting just below the warm top layer. Mix the two together and you dilute the fuel. But if the warm layer runs deep, there is no cold water to mix in. The storm stirs and finds only more heat. Studies from several peer-reviewed research teams, including work published in the Proceedings of the National Academy of Sciences, have shown that ocean heat now extends much further below the surface than earlier decades. Underwater waves generated by the storms themselves push heat roughly 4 times deeper than the mixing alone. Once it reaches that depth, it becomes trapped. It does not easily return to the surface. Future storms arriving in the same area still find warm water, even at levels where cold used to wait. That is the quiet shift. The safety switch is being unplugged by the storms that used to depend on it. Think of a campfire that somehow refills its own wood pile. Every log burned sends a signal back into the ground, and the ground pushes another log up. That is what a modern strong typhoon looks like in heat terms. It draws energy, mixes heat deeper, and in doing so preloads the ocean for whatever comes next. The feedback is slow, but over years, it stacks. Now put that in human terms. A storm approaches a coastline. Models predict a peak category, then a slight weakening before landfall. Families time their evacuations to those hours. Officials open shelters based on those hours. Power crews stage equipment based on those hours. Every decision leans on the old rule that storms run out of fuel near shore. When the fuel does not run out, decisions start breaking. The 2025 season showed this over and over in the Western Pacific. Typhoon Ragasa, which formed east of the Philippines in September, exploded into a violent super typhoon class system shortly after birth, then held that strength as it threaded between the Philippines and Taiwan. Flooding in Hualien County killed 14 people, with more than 150 reported missing in the initial aftermath. The storm kept its power longer than the old rules suggested. The old rules have not disappeared entirely, they have just been bent. And the strangest part is that the bending is still only half the story. Because a storm that holds its strength is dangerous. A storm that gains strength in the final hours before landfall is something else entirely. That is where rapid intensification begins. A tropical storm crosses a quiet stretch of ocean at dawn. By the next morning it is a monster. Sustained winds have jumped by dozens of miles per hour. The eye has tightened. Pressure has crashed. Entire evacuation plans drawn up the day before are now obsolete. This is rapid intensification. And it is the single phrase that keeps modern forecasters awake at night. The official definition is specific. The National Hurricane Center considers a tropical cyclone to be rapidly intensifying when its maximum sustained winds climb by at least 35 miles per hour in 24 hours. That is a serious change, enough to shift a storm one full category on the Saffir-Simpson scale, sometimes two. Enough to turn a manageable threat into a catastrophic one overnight. But the sharper worry is what meteorologists now call extreme rapid intensification. Climate Central defines it as a jump of at least about 58 miles per hour in the same 24 hours, not a nudge, a leap. Hurricane Milton in October 2024 is the textbook example of how extreme this can get. Over the southern Gulf of Mexico, Milton's sustained winds increased by about 95 miles per hour in a single day, according to the National Hurricane Center. Only Hurricane Wilma in 2005 and Hurricane Felix in 2007 strengthened faster in that basin. Milton's central pressure fell below 900 millibars, placing it among the most intense Atlantic hurricanes ever recorded. The Gulf water under Milton was at or above record-breaking warmth. That is the ingredient that made it possible. Zoom out and the trend is unmistakable. Research compiled by Climate Central shows that about 80% of major hurricanes, those at Category 3 or stronger, undergo rapid intensification at some point in their life. Between 1980 and 2023, 177 landfalling Atlantic tropical cyclones rapidly intensified above the 30-knot threshold. Nearly a quarter of those crossed the extreme line, and the frequency is climbing. The first working group of the latest Intergovernmental Panel on Climate Change report found that the global likelihood of a hurricane-force storm undergoing rapid intensification rose from about 1% in the 1980s to roughly 5% in recent years. A five-fold change in a single human generation. Here is what that means in plain human terms. A 48-hour evacuation window used to be a reasonable default. A family could watch a storm from a safe distance, measure the risk, pack slowly, drive inland the next morning. That buffer is now disappearing. A storm can cross the line from nuisance to catastrophe while people sleep. Forecasters are adjusting, models are improving. Satellite coverage is denser than ever, and aircraft reconnaissance flights, the hurricane hunters, send data back in real time. But even with every tool dialed up, the physics of the storm is outrunning the physics of the models in certain moments, particularly the ones that matter most. The final day before landfall, that is the forecaster's deepest fear. A Category 1 storm in the evening news, a Category 5 crashing ashore before breakfast. And the question behind all of this is now unavoidable. What exactly inside one of these storms flips the switch from slow growth to explosive growth in a matter of hours? The surface water alone cannot answer it. Something is happening inside the eye. The eye of a powerful storm looks peaceful from a satellite. A clean black dot at the center of a white spiral. On the ground beneath it, the wind drops for a few minutes. Sky turns pale. Birds sometimes land. People mistake that quiet for the end. It is not the end. It is the engine room. Around the eye, a ring of thunderstorms called the eye wall spins with the storm's highest winds. Inside that ring, rising columns of warm, moist air shoot upward at incredible speed, some of them climbing higher than any mountain on Earth. Scientists call these columns hot towers. They are the hidden machinery of rapid intensification. Here is how they work. Warm ocean water evaporates into the air near the surface. That moist air is lighter than the dry air around it, so it rises. As it rises, it cools, and its water vapor turns back into liquid droplets. That phase change releases heat, a lot of heat, into the air around it. The heated air rises faster, more water vapor is pulled up with it. The cycle accelerates. When one of these towers punches through the top of the storm, it unloads a massive burst of energy into the core. Researchers at the National Center for Atmospheric Research have shown that such bursts can trigger a rapid rearrangement of the cyclone's inner circulation. The storm tightens, spins faster, and climbs through categories in hours. Before satellite technology, no one could see these towers reliably. Now NASA missions like the Global Precipitation Measurement Mission scan through storms from orbit and map them in 3 dimensions. During Hurricane Milton, the radar on one of those satellites confirmed extremely tall towers inside the western eye wall during its peak. The storm was not just feeding on warm water, it was concentrating that energy in vertical bursts, like bellows on a forge. And that is where the mystery deepens. Scientists at the University Corporation for Atmospheric Research recently described 2 distinct modes of rapid intensification. The first is the familiar one, a storm in a friendly environment, warm water below and weak wind sheer above, that quietly explodes into a major hurricane. The second is stranger, a storm in unfavourable conditions, with strong upper-level winds trying to tear it apart, can still rapidly intensify through these same inner bursts. The bursts reorganise the circulation and override the hostile environment. That second mode is the one that catches forecasters off guard. It breaks the pattern. A storm that should be weakening is suddenly strengthening. The satellite image changes shape within a few frames. Numbers in the forecast discussion shift sharply. Picture an engine with 2 fuel lines. The first line runs through predictable conditions: warm water, calm sky. Forecasters can see it coming. The second line runs through something chaotic and internal, triggered by the storm itself. No current model can fully predict when that second line switches on. This is not a small gap in knowledge, it is the gap where the worst surprises live. Hurricane Michael, back in 2018, rapidly intensified over the Gulf of Mexico despite significant wind shear, because it passed over an anomalously warm pocket called a loop current eddy. Supercyclone Amphan did the same over the Bay of Bengal. Both storms caught communities with less warning than they should have had, so the eye is calm, but what spins around it is only partly understood. And the ocean itself, the original source of all that energy, is doing something forecasters only recently began to measure. Hundreds of feet below the surface of the tropical oceans, a hidden layer of warm water is expanding, quietly, year by year. You cannot see it from a ship. A swimmer could pass over it and feel nothing unusual, but a storm reaches straight into it. This is the deep reservoir, and it is the fuel tank forecasters did not fully account for until recently. Research presented at the American Geophysical Union's 2025 annual meeting pointed at something striking. The ocean regions that birth the strongest hurricanes and typhoons, particularly the North Atlantic and the Western Pacific, are not just warming at the surface, they are warming far below it. Some studies describe these as deep hot spots, regions where unusually warm water stacks hundreds of feet down, giving passing storms a fuel supply that simply did not exist in earlier climates. That same research suggests that human-caused climate change accounts for roughly 60 to 70% of the expansion of these deep hotspots. The rest comes from natural ocean cycles, but the human fingerprint is now the dominant hand. Think of the ocean as a house. In earlier decades, only the top floor was warm. Storms could burn through that floor in a day. Now the warmth has spread down through multiple stories. A storm sitting in one spot is no longer limited by a thin layer. It can keep drawing heat until something else stops it. Two of these deep hotspots matter most right now. One is off the Philippines in the Western Pacific. The other is in the Caribbean and the Gulf of Mexico. Both regions sit directly in the path of coastlines that are home to hundreds of millions of people. Both regions also sit in the historical track corridors of the world's most dangerous tropical cyclones. A Climate Central analysis during Hurricane Milton's formation showed Gulf sea surface temperatures running at or above record levels. A rapid attribution study found that those temperatures were made up to 400 to 800 times more likely by climate change during the weeks before Milton. An earlier analysis of Hurricane Helene, which struck just weeks before, concluded the ocean heat that fed it was made 200 to 500 times more likely by the same forces. These are not small adjustments. These are multipliers that shift the entire baseline of risk. And the deeper the reservoir, the more dangerous the final hours of a storm become. Because the last stretch before landfall is usually the one forecasters have counted on for weakening. Storms approaching a coast often cross a shelf of shallower, cooler water that drags their strength down. When deep heat reaches nearly up to the coast, that shelf no longer matters. Alex de Silva, speaking about the upcoming season, warned that sea levels at a depth of hundreds of meters in parts of the Caribbean can still reach around 80 degrees Fahrenheit. That is warm bath water, deep beneath the surface, sitting within striking distance of major coastal cities. Storms do not read property lines, they read energy. And the amount of energy now stacked beneath the surface of the tropics is the quiet story behind almost every headline about record-breaking typhoons. The surface is the theatre, the deep is the stage, and there is one more mechanism barely discussed outside research papers that makes the deep reservoir even more stubborn. A layer of water that acts like a lid. On the surface of the Western Pacific, in huge stretches of the tropical Atlantic, and across parts of the Caribbean, a hidden boundary sits in the water. It is not visible, it has no colour, but it keeps heat where heat wants to stay. Scientists call it a salinity barrier. In plain words, a salt lid. Here is the setup. In many tropical regions, heavy rainfall and river runoff dump huge amounts of fresh water into the ocean. Fresh water is lighter than salt water, so it floats on top, forming a thin, low salinity layer at the surface. Below that layer, the saltier, denser water stays put. Normally, waves and storms would churn these two layers together, bringing the cooler, saltier water up and cooling the surface. The salt lid blocks that churn. When a storm passes over a region with a strong salt lid, its winds can only mix the top freshwater layer. The deeper warm water, protected by the difference in density, stays largely untouched. The storm keeps drawing heat from a reservoir it cannot easily cool down. Research on tropical cyclones has repeatedly linked these salinity-driven stratifications with stronger rapid intensification events, including studies of storms over the Bay of Bengal, the Western Pacific, and the Caribbean. The Bay of Bengal is an extreme case. Rivers like the Ganges and the Brahmaputra pour enormous volumes of fresh water into a relatively small warm sea. The result is a persistent freshwater cap floating over deeper warm layers. When a cyclone crosses into this cap, the usual braking mechanism barely works. Cyclone Amphan in 2020 strengthened rapidly over exactly this kind of environment. The same pattern shows up during heavy monsoon seasons near the Philippines. In the Western Caribbean, tropical rainfall and the outflow of rivers like the Orinoco create similar freshwater pools that ride on top of warm, salty, deep water. In those pockets, the ocean cannot cool itself fast enough, and a passing storm reaps the reward. Picture a cup of hot coffee with a thin layer of cold cream floating on top. Stir the cup gently, and you only move the cream. The coffee underneath stays hot. Now imagine a storm as the spoon. Even a powerful spoon cannot reach the coffee if it is limited to the cream. The salt lid does something similar on a planetary scale, and this is where the picture gets more troubling. As the atmosphere warms, it holds more moisture, which leads to heavier rainfall over tropical oceans. Heavier rainfall means stronger freshwater layers in some regions. Stronger freshwater layers mean more persistent salt lids. More persistent salt lids mean storms encounter less cooling when they need to hit the brakes. One feedback piling onto another. None of this shows up cleanly in a weather map. That is part of why it has been so hard to communicate. But forecasters read it in pre-storm ocean data. They watch for places where the top layer is unusually fresh, or where the water below is unusually warm. When those signals line up with the developing cyclone, intensification forecasts lean toward the severe side for a reason. You have now seen 3 layers of the same engine: deep warm water, hot tower bursts, salinity barriers. Each would be enough on its own to make storms more dangerous. Together, they stack. And they do not just change how strong storms become, they change how fast those storms change. Which is why predicting a typhoon today is nothing like predicting 1-2 decades ago. For a coastal community, a forecast is more than a number on a screen. It is the schedule for when schools close, when planes stop flying, when hospitals move patients to higher floors, when grandparents get into cars and start driving inland. Forecast reliability is the backbone of every evacuation plan on Earth. That backbone is under stress. Over the past 2 decades, track forecasts, the predicted path of a storm, have improved dramatically. The National Hurricane Center and its partners around the world have cut average track errors roughly in half, thanks to better satellites, better computer models, and vast jumps in computing power. If the question is where a storm is going, the answer is sharper than ever. Intensity forecasts are a different story. For years, their accuracy barely improved. That gap is the exact place where rapid intensification hides. Predicting direction is hard. Predicting explosive change in strength over 24 hours is much harder. The storm's inner core, where hot towers bloom and the eye wall reorganizes, operates at scales smaller than most models can resolve cleanly. When Milton's winds jumped about 95 miles per hour in a single day over the Gulf, official forecasts before that run had not expected Category 5. Official discussions from the National Hurricane Center during the intensification explicitly described it as remarkable, with the pressure inside the storm crashing at a stunning rate. The models caught up, but the time between catching up and landfall was measured in hours, not days. In the Western Pacific, the 2025 season delivered similar jolts. Typhoon Regasa formed east of the Philippines in September and strengthened into the super typhoon class so quickly that regional warning agencies were forced to issue upgraded alerts on a compressed timeline. Typhoon 15, moving across eastern Japan at roughly 40 miles per hour after landfall, spawned a strong tornado in Makinohara City that damaged more than 1,000 homes and injured 74 people. Tornadoes from tropical systems are notoriously difficult to predict more than a short window in advance. Every one of those outcomes had forecasters chasing the storm rather than leading it. There is also a subtler failure mode. A storm can stall, a storm can wobble, a storm can skip a predicted landfall point by 30 or 40 miles at the last moment. When intensity is rising rapidly and track is shifting slightly, those small shifts hit different neighborhoods, different hospitals, different coastlines. Evacuation routes crafted for one corridor become useless when the storm turns. Picture the forecast as a flashlight beam projected into the future. A narrow, steady beam is useful. A beam that widens and flickers just when you need it most is not. Rapid intensification widens the beam at the worst possible hour. This is not a story about forecasters failing. They are working with some of the hardest physics on the planet, under time pressure, in front of audiences of millions. It is a story about the physics itself shifting faster than tools can fully track, even as those tools get better every year. And there is one more layer of difficulty. Climate-driven warming does not just make storms stronger. It can also shift where rapid intensification happens, closer to coasts, closer to landfall, where the warning gap hurts most. A storm that blows up 500 miles offshore is a meteorological drama. A storm that blows up 100 miles offshore is a civil defense emergency. To close that gap, scientists have turned to a new kind of tool, one that does not think like a physicist at all. A hurricane forecast at its heart is an equation. Air pressure, temperature, humidity, rotation, all tracked across a grid that covers the planet. For decades, the best models on Earth have solved those equations using pure physics, step by step, on some of the largest supercomputers ever built. Now something new has joined the table. Machines that do not solve equations at all. They pattern match. In 2025, independent evaluations of an artificial intelligence weather model built by a major research lab found that it often matched, and sometimes beat, top operational forecast systems on hurricane track and in some cases intensity. It did this by learning from enormous archives of past weather, recognizing patterns, and projecting forward without running the physical equations step by step. What once took us supercomputer hours could be produced in seconds on a far smaller machine. That shift is rearranging how forecasters think about rapid intensification. Traditional models stumble on the inner core of a storm because the scale of the physics there is very small, and computing the equations finely enough across the whole globe is expensive. A learning model, trained on decades of observed storms, may recognize a hidden signature in the larger environment that almost always precedes explosive strengthening. It cannot explain why, but it can flag the pattern hours earlier. In cases reviewed during the 2025 Atlantic and Pacific seasons, some artificial intelligence guidance pinged intensification earlier than traditional systems. It was not perfect. It sometimes missed. But the trend was promising enough that major weather agencies began incorporating machine learning outputs alongside their legacy models as experimental guidance. Here is the key phrase: alongside, not in place of. Because a pattern matcher without physics cannot truly explain. It can flag, it can warn, it can give forecasters a reason to look closer, but the physical models remain critical for understanding why a storm behaves the way it does, and for testing what might happen under conditions never seen before. An unprecedented warming future is exactly the kind of condition the machines have the least data on. There is another quieter use for these tools. They can scan vast streams of satellite data for subtle changes in a storm's shape, a slight tightening of the eye, a new band of thunderstorms forming in a specific quadrant, a warming spot at the top of a cloud tower, things a tired forecaster working a 12-hour shift might miss. Machines do not get tired. A good comparison is medicine. Physicians still make final diagnoses, but modern imaging software flags patterns a human eye might overlook. The best outcomes happen when both work together. Storm forecasting is moving the same direction, and all of this matters for one reason that keeps returning to the centre of the story: time. Every additional hour of warning before a rapid intensification event is an hour in which a town can close, a highway can empty, a coast can quiet down. Cutting even half a day off of the surprise can be the difference between a manageable disaster and a generational one. The 2026 Atlantic season is projected by AccuWeather to bring 11 to 16 named storms, 4 to 7 hurricanes, and 2 to 4 major hurricanes. A developing El Niño is expected to tamp down some late-season activity, but the deep warm water is not going anywhere. And all three of the major seasonal outlooks agree on one thing: storms capable of serious damage will form somewhere. The only real question is where and how fast, because the coasts are not facing just stronger storms. They are facing storms that arrive with more water than ever before. Wind gets the headlines, water takes the lives. Historical data from hurricane landfalls around the world tells the same story again and again. Most deaths in a tropical cyclone do not come from the wind directly. They come from water, from storm surge, the wall of ocean pushed ashore by the storm, from rainfall, the sheets of water dumped inland for days, from the slow, creeping rise of rivers fed by that rainfall. And both of those water threats are being amplified by the same forces driving rapid intensification. Start with storm surge. A tropical cyclone is essentially a giant low-pressure system with a wall of wind on its edges. As those winds drive toward a coastline, they push a dome of seawater ahead of the storm. When that dome meets shallow, sloping coastal waters, it piles up, sometimes to heights of 10, 15, even 20 feet above normal sea level. A Category 3 hurricane passing over Tampa Bay was projected during Milton's approach to drive surge of up to 12 feet in vulnerable zones. Storm surge is not just about how strong a storm is at landfall, it is about how strong a storm has been in the hours before landfall. A hurricane that spent an extra day at Category 5 status offshore pushes a much larger dome of water ahead of it. Even if it weakens to Category 3 just before the coast, the water is still on the move. The surge does not weaken at the same rate the wind does. Rising sea levels, already pushed up by decades of warming oceans, add a baseline to every surge event. Inches matter. A modest global rise adds inches to the baseline that a storm then stacks on top of. Neighbourhoods that historically never flooded now flood during storms that would have been unremarkable 50 years ago. Then there is rainfall. A warmer atmosphere holds more moisture. For every 1 degree Fahrenheit rise in temperature, the air can carry a few more % of water vapour. A tropical cyclone is a machine for wringing that moisture out of the sky. When these storms move over land, they release it in staggering quantities. Hurricane Helene in 2024 is a clear modern example. Before its direct winds even arrived in many inland areas, bands of rain had already dropped feet of water on communities in the southern Appalachian Mountains. Rivers swelled into valleys where they had not reached in living memory. Bridges collapsed. Entire towns were cut off. Helene's rainfall totals combined with ocean-warmed humidity turned a coastal hurricane into an interior catastrophe. And here is the twist that catches people off guard. Storm-related water threats can travel hundreds of miles from the coast. You do not need to live near the ocean to be in a hurricane or typhoon's water footprint. Flash flooding, landslides on saturated slopes, and slow-moving river crests can appear days after the wind has died. Picture a storm as a sponge travelling across the atmosphere. The warmer the world, the bigger the sponge. It soaks up more water over warm oceans, It wrings that water out as it moves inland. When the sponge is larger than usual, the zones at risk are larger than usual too. For coastal emergency planners, this changes everything. The old mental map, where the coast faces wind and surge and the interior watches from safety, no longer fits. Everyone inside a certain radius is now in the water threat zone, and the widening of that zone is one of the clearest trends in recent cyclone behaviour. Yet the wind matters too, because something has quietly changed about the top end of it. The Saffir-Simpson hurricane wind scale, the system used in the Atlantic and Eastern Pacific, has 5 categories. Category 5, the top, begins at sustained winds of 157 miles per hour. Above that line, the scale simply says catastrophic. There is no Category 6. Some scientists now argue there should be. The argument is not rooted in drama, it is rooted in data. Over the past decade, several tropical cyclones have reached sustained winds well above the Category 5 threshold, in some cases approaching or exceeding 190 miles per hour. These are storms that blow past the current top of the scale and keep climbing. Patricia in the Eastern Pacific in 2015, Dorian over the Bahamas in 2019, and several Western Pacific super typhoons have all pushed into territory where the difference between a low Category 5 and the strongest observed winds is as large as the difference between Category 3 and Category 5. Research discussed around the 2025 American Geophysical Union meeting pointed out that more than half of the hurricanes and typhoons that exceeded a hypothetical Category 6 wind threshold in the historical record have occurred in just the past decade. That is not a long trend line, it is a short, steep one. Proponents of a Category 6 argue that the current top of the scale blurs too much variation. A storm with 160 mph winds and a storm with 190 mph winds are both labelled Category 5, even though the destructive potential is drastically different. Wind damage does not scale linearly with wind speed. It scales much more steeply. A jump from 160 to 200 miles per hour can multiply damage dramatically, especially for engineered structures. Opponents raise a different concern. They worry that adding another category could send a misleading message. Could people assume that a Category 4, now further from the top of the scale, is somehow safer than before? Evacuation decisions are already shaped by category labels. Changing the ceiling could confuse behaviour at the lower rungs. There is also the point that for most coastal communities, any hurricane above Category 3 is catastrophic. Arguing about new tiers matters less than making sure people respect the tiers we already have. But the scientific argument is growing harder to ignore, because the existence of storms worthy of a theoretical Category 6 is not a fringe claim. It is an observation made with satellites and Hurricane Hunter aircraft and dropsondes. Those storms are real, they are forming in measurable numbers, and the same deep hotspots that feed rapid intensification appear to be clustering near the regions where these strongest storms are born. Picture a speedometer on a car that only goes up to 100. Most of the time, that is fine. Drivers rarely exceed it. Now imagine the highway speed limit in certain areas has quietly shifted. More and more cars are pushing past 100. The speedometer still pins at the top no matter how fast the car actually goes. Drivers reading the dial get incomplete information. The same design limit is appearing in the way we label storms. Whether a new category is formally added or not, the underlying trend matters more than the label. The top end of tropical cyclone intensity is not just shifting, it is opening a gap between what the scale can describe and what the ocean can produce. And that gap runs straight into the lives of the people living on the coast. particularly in the coastlines most exposed to the deep hotspots. Of all the ocean basins on Earth, one produces more, stronger tropical cyclones than any other, the Western Pacific, and it is where the newest rules of this planetary weather system are being written. This basin runs from the waters east of the Philippines, through the seas around Taiwan and Japan, up along the coast of China and out into the open Pacific. It sits directly atop one of the deepest pools of warm water on the planet, a place nicknamed the Warm Pool. In this region, sea surface temperatures regularly exceed 86 degrees Fahrenheit for months on end, and the warm water extends hundreds of feet down. This is the home basin of the super typhoon. Historically, the Western Pacific produces roughly a third of the world's total tropical cyclones in an average year. Many of these become intense. In the 2025 Pacific typhoon season, according to the Japan Meteorological Agency, 27 typhoons formed, the highest count in 6 years. The season ran long, with significant activity spilling into September and October. Rapid intensification featured prominently. So did erratic tracks that did not follow standard forecast patterns. Typhoon Regasa in September was a textbook case. The storm formed east of the Philippines, strengthened into the super typhoon class almost immediately, and threaded its way between the Philippines and Taiwan while maintaining extreme intensity. Flooding in Hualien County killed 14 people, with more than 150 reported missing in the initial count. Typhoon 15, later in the same season, approached eastern Japan and behaved strangely. It accelerated after landfall, travelling at roughly 40 miles per hour while spinning out highly localized extreme weather. A strong tornado struck Makinohara City, damaging more than 1,000 homes and injuring 74 people. Tornadoes from typhoon-related storm bands are one of the most difficult short-fuse threats in all of weather prediction. Zoom out and the pattern is clear. The Western Pacific is not just hosting more storms, it is hosting storms that behave in ways outside of the historical playbook. The Philippines alone sits in a geographic crosshairs. The archipelago is one of the most storm-exposed nations on Earth. A typhoon entering the Philippine area of responsibility can encounter warm water, low shear, and a fresh supply of moisture all within a short distance. Once it clears the islands, many of those same storms find favourable conditions in the South China Sea and barrel towards southern China and Vietnam. Vietnam's meteorologists heading into 2026 have publicly warned that although the total number of storms might be lower than in recent record years, the risk of very strong and unusual storms remains high, especially due to elevated sea surface temperatures. Japan, Taiwan, South Korea, and China all face similar calculus. Each country has built elaborate warning systems, improved infrastructure, and rehearsed evacuations for decades. Those systems work. They save lives every year. But they were calibrated for one kind of storm, and they are now encountering another. Picture a region covered in well-built dams, each rated for a certain river flow. Now imagine the average river flow steadily increasing. The dams still hold, most of the time, but the margins shrink, and every time a storm pushes into the upper tail of the new distribution, it pushes closer to failure. The Western Pacific is where those margins are being tested hardest. Not because its forecasters are weaker, because the conditions are stronger. And while Asia watches that frontier, another stretch of ocean half a world away is developing a twin. Across the Caribbean Sea, looping between the islands and the coasts of Central and South America, a warm current flows year after year. The Caribbean Current. In the Gulf of Mexico, this water bends northward and becomes the Loop Current, a meandering river of warmth inside the Gulf. Occasionally, the loop current pinches off a rotating pool of hot water called an eddy. These eddies are small. They are often only a few hundred miles across. They can drift slowly, sometimes lingering in the central or western Gulf for months. And when a hurricane wanders over one of them, the consequences can be extreme. Loop current eddies are deep, warm water concentrated into a small circle. A passing hurricane can draw energy from a pool that reaches well below the surface, maintaining or gaining strength even when the surrounding atmosphere looks unfavourable. Hurricane Michael in 2018 is a specific case. Michael rapidly intensified across the Gulf of Mexico despite strong vertical wind shear, partly because it crossed water with anomalously high heat content, including loop current-linked features. The storm slammed into the Florida Panhandle as a Category 5. For decades, that part of the coast had never recorded a Category 5 landfall. This is why Caribbean and Gulf forecasting has become a multi-layered game. It is not enough to track the atmosphere. Agencies now watch ocean heat maps in near real time, looking for eddy positions, freshwater plumes, and subsurface warm anomalies. When a developing storm's forecast path threads near one of these features, intensity guidance shifts upward. The Caribbean also deals with something called the Central American Gyre. This is a seasonal, large-scale area of low pressure centered over Central America that can funnel moisture and spin up tropical systems in the southwest Caribbean. Both Helene and Milton in 2024 were influenced by interactions with this gyre. In Milton's case, the storm emerged from the Bay of Campeche and took an unusually east-northeastward track across the southern Gulf, crossing record-warm water before striking Florida. The geography of the region compounds the danger. The Gulf of Mexico is a nearly enclosed sea, ringed by coastlines that are densely populated. Storms spinning across it rarely have far to go before they hit land. A hurricane rapidly intensifying near the Yucatan Channel can reach the coasts of Texas, Louisiana, Mississippi, Alabama, or Florida within a day or two. Now imagine a region-wide setup. Warm water from the tropics flowing in, loop current looping through the Gulf, eddies pinching off into deeper basins, freshwater plumes from rivers like the Mississippi adding salt lids. All of these features operating at different scales, overlapping in patterns that shift week by week. Into that environment, a tropical system walks, even a weak one. It crosses one eddy and strengthens. It crosses a freshwater plume and loses its self-cooling. It finds a window of low wind shear and explodes. The combination is why the Caribbean and Gulf have hosted some of the fastest intensification events ever measured, including Wilma in 2005, Felix in 2007, Michael in 2018, and Milton in 2024. Heading into the 2026 Atlantic hurricane season, AccuWeather's forecast specifically highlights the northern and northeastern Gulf Coast and the Carolinas as areas at the greatest risk of direct impacts. The reasoning behind that focus traces directly back to the deep, warm water, the loop current system, and the pattern of recent storms. And the storms do not care about the calendar, or the category, or the forecaster's best efforts. They care about energy, and the energy is waiting. That waiting energy does not only matter when a storm is already forming, it matters when a storm is deciding whether to form at all. Every tropical cyclone has a checklist. Warm water, moist air, low wind shear, a pre-existing disturbance to spin around, and distance from the equator. If even one of those ingredients is weak, the storm usually fails to develop. Usually. Over the past several years, forecasters have watched something unusual. storms forming in conditions that should not have supported them, tropical systems spinning up in parts of the ocean where climate records call such spin-ups rare, cyclones strengthening despite wind shear that traditionally would have torn them apart. Hurricane Otis in 2023 is one of the most jarring modern examples. A tropical storm for most of its life, Otis found itself over warm Pacific water off the coast of Mexico and exploded. Within about 24 hours, its sustained winds jumped from roughly 65 miles per hour to near 160 miles per hour. It slammed into Acapulco as a Category 5 with almost no time for evacuation. The official forecasts in the hours before had Otis as a much weaker storm. Ocean heat content and atmospheric alignment bridged the gap. In the Arabian Sea, cyclones were once rare. That sea was considered a marginal basin, with conditions usually unfriendly to strong storm development. In recent decades, that has been changing. The Arabian Sea has produced multiple intense cyclones in recent years, with storms reaching category levels unusual for the region. Warmer surface and subsurface waters appear to be tilting the local balance. The Bay of Bengal, already known for its cyclones, has seen its share of monsters. Cyclone Amphan in 2020 intensified rapidly even as wind shear increased because of the underlying marine heat wave. Researchers publishing in major science journals have noted that extreme ocean temperatures associated with marine heat waves can compensate for atmospheric conditions that would ordinarily suppress intensification. In the South Atlantic, which has historically been considered nearly storm-free, the rare tropical cyclone occasionally appears now. Katrina back in 2004 was the first confirmed hurricane-strength storm to strike Brazil. Since then, a handful of other tropical or subtropical systems have spun up. The frequency remains very low, but what was once considered impossible has slipped into the category of uncommon. Each of these cases is limited. Each is the subject of active scientific debate. No single storm proves a trend, but together they sketch a pattern. The edges of the world's cyclone basins are blurring. Regions long considered safe boundaries now occasionally step across those lines. Picture an old map with safe and dangerous zones painted in different colours. For generations, the colours stayed roughly in place. Now, the line between them is wavering. Regions that used to be solidly safe have faint, dangerous stripes appearing inside them. The shading is not symmetric. Some zones are growing, a few are contracting. The overall map is losing the crisp edges it used to have. For people living on those edges, the practical meaning is subtle but real. Building codes, insurance structures, and emergency plans are all written to historical climatology. Historical climatology is a moving target now. A coastal town on the edge of the traditional typhoon belt may face a once-in-a-century storm that decades ago would have been closer to once in 5 centuries. Planning for one does not necessarily prepare for the other. The storms that should not have formed are the canaries. They show where the broader system is stretching. And the stretching is not limited to new regions. Inside the classic cyclone basins, something else is happening. Storms that do form are behaving differently on their way to land. They are stalling. A typical hurricane or typhoon moves. That movement matters. As a storm passes over a region, it dumps rain for a few hours, then moves on. The wind drops, the sky clears, cleanup begins. But a growing number of tropical cyclones are refusing to move. Studies of storm tracks over recent decades show that the forward speed of many tropical systems has slowed. Some have stalled for days over a single region, parking their rain bands over one area and releasing catastrophic rainfall totals. Hurricane Harvey in 2017 is the defining modern example. Harvey hung over eastern Texas for days, dropping more than 50 inches of rain in some locations. The storm's wind damage was significant. Its flooding damage was historic. Harvey was not alone. Storms over the western Pacific have stalled. Storms over the Bay of Bengal have stalled. Storms over the Atlantic have stalled. Each case has its own causes, but researchers have identified broader shifts in atmospheric steering currents that can allow tropical systems to linger longer than they used to. Here is why it matters. Rainfall is essentially a rate multiplied by time. A storm moving at 20 miles per hour delivers moderate rainfall totals across a wide corridor. A storm moving at 5 miles per hour delivers massive totals across a narrow one. A storm that stops entirely can unload absurd amounts of water on a single city. Combine that with a warmer atmosphere capable of holding more moisture, and the math gets ugly fast. A slow storm is not just a slow storm. It is a slow storm delivering heavier rain than a fast storm ever could. Every hour added to its time over a populated area adds inches to the rainfall totals. Stalled storms also amplify storm surge timing. Surge is not a one-time wave. It is a sustained pile-up of ocean water driven against the coast. If a storm sits offshore for an extra 12 hours, it keeps pushing water inland for an extra 12 hours. Tides cycle in and out during that window, and surge riding on top of a high tide can overtop seawalls that would otherwise hold. The reasons for slowing forward motion are still under active study. Some research links it to weakened atmospheric steering flows, particularly in the mid-latitudes. A high-pressure system that would have shoved a hurricane forward can now fade or drift differently, leaving the storm with no clear direction. Other research points to shifts in the jet stream, which can change how tropical cyclones interact with mid-latitude weather patterns. The result for a coastal resident is unsettling. A storm that might have been a severe 12-hour event now becomes a 2 or 3 day siege. Power outages last longer. Rescue operations stretch thinner. Rivers crest after the storm has technically departed. Cleanup gets pushed back by days. Picture a hose pointed at your roof. A fast sweep across the roof might leave the surface wet. A slow sweep soaks a section. A hose held still over one spot will find weaknesses that the fast sweep never would have. The roof fails where the hose lingered. Stalled cyclones are the lingering hose, and stalling is just one of several newer track oddities. Some storms are looping back on themselves. Some are making landfall, weakening, then re-intensifying over warm waters on the other side of a peninsula. Forecasters have watched these behaviours grow more common enough to build new model experiments around them. Climatology used to be a solid floor. Now it feels in places like a raft. Still useful, still supportive, but aware of every swell, and the consequences ripple inland. When a hurricane or typhoon makes landfall, the wind is only part of its delivery system. Tucked inside the outer rain bands, often far from the eye, another kind of storm can spin up, a tornado. This detail surprises people. The image of a tropical cyclone is usually a spiral on a satellite, not a funnel cloud at ground level. But tornadoes are a well-documented hazard in many landfalling tropical systems. They appear with little warning, often in the outermost right-side bands of a storm in the northern hemisphere, where wind shear and low-level rotation combine with the cyclone's inflow. In the 2025 Western Pacific season, Typhoon 15 moved across eastern Japan and triggered a strong tornado in Makinohara City. Classified as a JEF 3-class tornado on the Japanese enhanced Fujita scale, it damaged more than 1,000 homes and injured 74 people. Local forecasters, working with short lead times, faced the challenge of identifying precisely which rain bands were most likely to rotate. These are among the most difficult predictions in weather science. Atlantic storms produce similar hazards. Hurricane Milton's approach to Florida in October 2024 spun off multiple tornadoes well ahead of the main wind field, with parts of eastern and central Florida experiencing damaging tornadic activity hours before the hurricane's own eyewall arrived. Warning offices issued tornado alerts alongside hurricane warnings. Here is what makes these tornadoes tricky. They tend to be short-lived and fast-moving. They form in environments where the atmosphere is already saturated, which makes visible identification harder. Radar can see rotations, but warning times are often measured in minutes, not tens of minutes. A community bracing for hurricane winds suddenly finds itself facing the very different pattern of a tornado warning, with different safety instructions, different shelter locations, and different timelines. On top of that, tornadoes often appear outside the obvious target zone. A city on the edge of a hurricane's forecast cone expecting only heavy rain can be the one that gets the tornado outbreak. A more distant coastline can experience relatively calm conditions while the storm spins up funnels inland. This decoupling between where the wind is strongest and where tornadoes appear complicates evacuation messaging. Research on tropical cyclone-spawned tornadoes shows that the most favourable environments for them develop in the forward right quadrant of a landfalling storm due to enhanced low-level wind shear in that region. Forecasters focus their tornado watches accordingly, but local terrain, interactions with other weather systems, and even small changes in the storm's track can shift those zones. Imagine a marching band moving down a street. The drums are loud and obvious, but tucked into the formation, a single bell player adds sharp notes at unpredictable moments. You can hear the drums for blocks. The bells catch you by surprise, even though they are right there in the formation. Tornadoes inside a cyclone work a bit like that. The main story is the storm. The bells are the funnels. There is another subtler dynamic at work. A warmer, moister atmosphere not only feeds a stronger main storm, it can also feed more vigorous outer rain bands, which may contain more of the rotation needed to seed tornadoes. The science here is still developing, but the hint is that the same drivers pushing rapid intensification may also be extending the tornado-producing reach of these storms inland. That is why a tropical cyclone landfall is no longer just a coastal event. It is a regional event that can include tornado outbreaks hundreds of miles from the beach, and that regional reach points to another shift that is reshaping the entire conversation. Lead times. A good hurricane forecast has two deliverables: where the storm is going and when it will arrive. The second one, timing, is the one that matters for a family deciding when to get in the car, when to pull the plywood out of the garage, when to leave. In an era of rapid intensification, those timing deliverables are being squeezed. Here is the specific problem. Traditional emergency management relied on a pyramid of lead times. 3 or 4 days out, a general alert, 2 days out, specific warnings, 1 day out, final evacuations. Storms usually reached peak strength offshore, then weakened slightly as they approached land. Planners had time to react to the worst case and adjust downward if the storm eased. That pyramid is now under pressure. Imagine a storm that is a tropical storm 36 hours before landfall. Alerts go out. Communities prepare. Officials estimate a landfall intensity of Category 2. Evacuation orders are scaled to that level. 24 hours later, the storm has undergone extreme rapid intensification. It is now a strong Category 4 aimed at the same coastline. Suddenly, the evacuation zones drawn for Category 2 are badly undersized, but there are only 12 hours left before landfall. In those 12 hours, highways cannot absorb new evacuation traffic at full scale. Hospitals cannot relocate intensive care patients cleanly. Nursing homes face impossible choices. Gas stations run out. Cellular networks slow. People who would have left calmly 2 days earlier now face dense traffic, panic buying, and closing evacuation windows. This is the scenario forecasters dread. It is no longer hypothetical. Hurricane Otis in 2023 is a brutal example. Before its rapid intensification over the eastern Pacific, Otis was forecast to make landfall near Acapulco as a tropical storm. Within roughly a day, it blew past Category 3, 4, and 5, striking Acapulco with catastrophic winds. Evacuation and shelter preparation timed for a lesser storm were overwhelmed. The physical and economic losses were severe. Hurricane Milton gave the Gulf Coast its own brush with this compressed timeline. Milton went from tropical storm strength to Category 5 in about a day over water, made unusually warm by climate change. Forecasters caught the intensification promptly, but the speed of the escalation forced officials to refine evacuation orders within hours, not days. Highways in parts of Florida backed up. Fuel deliveries struggled to keep pace. Most people got out in time thanks to strong coordination, but the margin was tight. Picture a bank teller with a line of customers. If every transaction takes 2 minutes, the line flows. If the teller's time per transaction suddenly doubles, the line backs up. The total number of customers never changed. The bottleneck changed. Evacuations face the same bottleneck math when lead times shrink. Emergency managers are adapting. Some coastal states and countries have moved to earlier, more conservative evacuation orders, triggered by the possibility of rapid intensification, not just the current forecasts. Some communities have invested in more robust shelters, redundant fuel logistics, and pre-positioned emergency crews. These efforts help, but they cost money, political will, and practice. There's also a human factor that runs underneath every technical solution: evacuation fatigue. When people evacuate repeatedly for storms that turn out milder than feared, trust in warnings erodes. When the next rapid intensification event hits, some of those people may stay home. The population of storm-experienced coastal residents now includes some who remember the close call that turned, and some who remember the false alarm that felt wasteful. Forecasters know this. That is why the push to detect rapid intensification earlier is more than a scientific puzzle. It is a social one. Because when the science runs out of time, communities pay, and the final question climbs over all of the others. Everything in this story has led back to one substance: warm ocean water. Deep, heat-loaded layers stacked hundreds of feet beneath the surface, expanding in area, persisting longer in the calendar, inching closer to populated coastlines. The uncomfortable finding from recent research is that the storms themselves are helping to deepen that warmth. Work published in the Proceedings of the National Academy of Sciences examined subsurface ocean measurements before and after 3 hurricanes. The team found that underwater waves generated by the storms transport heat roughly 4 times deeper into the ocean than direct mixing during the storm. That heat, once pumped downward, is not easily released back into the atmosphere. Ocean currents can then transport it thousands of miles, embedding it into the larger climate system. In the short run, this finding has a silver lining. Heat buried in the deep ocean is not heat warming the atmosphere. In the narrow sense of atmospheric temperature, hurricanes may slightly slow down surface warming by stashing heat where it cannot easily escape. But in the longer run, the picture is darker. That buried heat does not vanish. It circulates. It eventually returns to regions where tropical cyclones form. The exact routing is not fully mapped. The paper suggested that heat from typhoons in the Philippine Sea may, over years, flow through equatorial Pacific currents toward the coasts of Ecuador or California. Other studies trace similar long trajectories for Atlantic storm heat. This means a major hurricane or typhoon is not just a single event. It is an event that seeds the ocean for future events. It tops up the deep reservoir. It preloads the fuel tank. A season of strong storms in one year can quietly contribute to stronger storms in future years. A separate set of studies, synthesized at the American Geophysical Union meeting in 2025, attributes roughly 60 to 70% of the expansion of deep ocean hotspots to human-caused climate change, with the remainder driven by natural cycles. On top of that baseline, the storms themselves act as pumps, redistributing heat in ways that keep it sequestered in the tropics. Picture a thermostat tied to a faulty feedback loop. Warm air is supposed to trigger cooling. Instead, every cooling attempt generates more warm air. The system never quite stabilizes. It drifts slowly in one direction. Earth's tropical oceans are not quite that broken, but the feedback from hurricane-driven heat storage is one more brick in a wall of forces pushing warmth deeper and keeping it there. And the practical consequence is simple. Even if global emissions slowed dramatically, the heat already stored in the deep tropical oceans would continue to fuel stronger storms for decades. The ocean remembers. It remembers in temperature. It remembers in salinity. It remembers in the positions of currents and eddies that shape future storm tracks. This is the feedback that keeps climate scientists up at night. Not because it is a surprise, because it is so patient. A warming feedback that operates on the timescale of decades is very hard to interrupt. It does not respond to emergency actions in weeks. It shifts on the scale of generations. For a coastal resident, this layer is distant but inescapable. Every new super typhoon that pumps heat into the Philippine Sea is contributing to the fuel that the next one will find. Every Gulf hurricane that buries heat below the loop current is loading the next loop current eddy. The storms are not only consumers of ocean heat, they are also, in a smaller but meaningful way, builders of it. Understanding this feedback does not change the forecast for any one storm, but it changes how we read the trajectory, and it changes the meaning of what the forecasters are truly terrified of. Because the threat behind the typhoon is not the typhoon, it is everything the typhoon is feeding. Picture a stretch of ocean roughly the size of a small country, sitting east of the Philippines, holding more heat in its depths than almost anywhere else on Earth. This is a hotspot in the most literal sense, not a region of warm surface water alone, a region where warmth runs deep, wide, and persistent. Scientists studying deep ocean hotspots have identified this patch as one of the most consequential on the planet. Research associated with the American Geophysical Union's 2025 meeting highlighted two regions in particular where deep hotspots are expanding fastest. One is off the Philippines in the Western Pacific. The other is in the Caribbean. Both sit directly in the paths of the world's most storm-exposed coastlines. The Philippine hotspot is the launching pad for many of the strongest tropical cyclones ever recorded. Super Typhoon Haiyan in 2013 drew its strength from these waters before slamming into the central Philippines as one of the most intense landfalling storms in modern history. The 2025 season produced Typhoon Ragasa, which intensified into the super typhoon class almost immediately after formation and held that strength for days. Here is what sets this hotspot apart from a normal warm patch. Its thermal structure runs hundreds of feet down. Cooler water that would normally appear at modest depths sits much lower here. A storm passing over it can churn for an unusually long time without cooling its own fuel supply. And the warm water is not just warm, it is warm enough, deep enough, to support the theoretical ceiling of tropical cyclone intensity. Meteorologists describe something called the maximum potential intensity. This is the strongest wind speed a hurricane or typhoon could achieve given the surrounding atmospheric and ocean conditions. Most storms never reach this ceiling. They run out of time, or run into shear, or hit land first. But in regions where the ceiling itself is climbing, the rare storm that approaches it has more room to grow. The Philippine hotspot has been raising that ceiling for years. The human consequences are stark. The Philippines is home to more than 110 million people, spread across an archipelago of more than 7,000 islands. Many coastal communities sit within a few feet of sea level. Evacuation is complicated by geography. Every typhoon season, millions of Filipinos move inland or to higher ground, sometimes multiple times in the same month. Taiwan, Japan, southern China and Vietnam share the downstream effects. A typhoon born over the Philippine hotspot often survives its encounter with the islands and re-energizes over the South China Sea or the waters near Taiwan. A second round of rapid intensification is not unusual. A storm that appeared to weaken while crossing Luzon can rebuild into something formidable before hitting another coastline 24 hours later. Think of the hotspot as a great field of embers. Any passing storm that drops sparks finds kindling ready. The embers do not cool between storms because the deep heat is replenished by ocean currents and trapped by salinity layers. Year after year the field stays hot, the storms keep coming, and the field is growing. Recent observations suggest that the area of the Western Pacific with deep warm water, conducive to extreme intensification, has expanded over the past few decades. That expansion pushes the high-risk zone closer to coastlines that once sat on its edge. The Caribbean twin of this hotspot shares many of the same traits, and it has its own history of making a certain kind of coastline famous. The Gulf of Mexico is a small sea compared to the vast Pacific. At its widest, it spans about 1,000 miles. A storm crossing it can traverse its full width in a day or two, which means the Gulf gives hurricanes almost no cooling off distance before landfall. Now, load that small sea with a deep pool of heat, and the physics becomes unforgiving. In recent years, sea surface temperatures across the Gulf have repeatedly reached record-breaking levels, sometimes exceeding 88 degrees Fahrenheit for weeks at a time. The depth of that warmth has grown. Rapid attribution studies have linked this to human-caused climate change with striking statistical force. Gulf water temperatures during Hurricane Helene's approach were found to be made 200 to 500 times more likely by climate change. For Milton, the multiplier ran up to 400 to 800 times more likely. These numbers are not rhetorical. They are the output of detailed simulations comparing today's climate with a counterfactual version of Earth, without human-caused warming. The message is consistent. The Gulf of Mexico that is fueling modern hurricanes is not the same Gulf that fueled storms even a few decades ago. Inside this warmer Gulf, a complex circulation system runs. The loop current carries warm water from the Caribbean north, curls through the eastern Gulf and exits through the Florida Straits. Periodically, the loop current sheds large rotating eddies of warm water, which can drift for months in the central Gulf. Each eddy is a deep reservoir in miniature, a pocket where ocean heat content is especially high and especially persistent. A hurricane that crosses one of these eddies can undergo dramatic intensification even when the surrounding environment looks only modestly favourable. Hurricane Michael in 2018 did precisely that, becoming a Category 5 at landfall on the Florida Panhandle. Hurricane Rita in 2005 rode similar warm features. Hurricane Katrina drew energy from Gulf waters and loop current-related structures before devastating the northern Gulf Coast. Modern forecast tools now display ocean heat content maps alongside traditional sea surface temperature charts. When a forecasted storm track crosses an eddy, meteorologists adjust their intensity outlooks accordingly. This is one of the real forecasting improvements of the past decade. But improved mapping does not cool the water. There is also the matter of geography. Major population centers ring the Gulf: Houston, New Orleans, Mobile, Tampa, Miami on the adjacent Atlantic side, Havana, Merida, and countless smaller towns. Oil and gas infrastructure clusters offshore. Shipping lanes thread through. An intense hurricane in the Gulf does not just threaten lives. It threatens a chunk of the global energy and trade system. Picture the Gulf as a shallow frying pan with a ring of cities along its rim. The pan is hot. The food in it, any passing storm cooks very fast. And the cities have nowhere to retreat to. They sit on the rim. That geometry is what makes the Gulf's warming so consequential. It is not just that storms here can intensify. It is that they have no time or distance to slow down before reaching a populated coast. A storm forming in the Bay of Campeche or the northwestern Caribbean has 1 or 2 days of open water at most before striking a major shoreline. AccuWeather's 2026 outlook flagged the northern and northeastern Gulf Coast as among the highest risk zones for direct impacts. The reasoning is layered. Climatological patterns similar to 2009, 2014, 2018 and 2023, plus the deep warm water, plus the coastline geometry. All of it stacks up into one forecast theme. The Gulf remembers its heat, and the storms remember the Gulf. On land, a heat wave is a visible event. Streets shimmer, schools close, rivers shrink. People talk about it on the evening news. In the ocean, a heatwave is invisible. No headlines, no shimmer. But it changes everything about how storms behave. A marine heatwave is a prolonged period of unusually warm sea surface temperatures, typically lasting for weeks or longer, and often extending below the surface. In recent years, marine heatwaves have become more frequent, more intense, and more widespread across the world's oceans, driven by a combination of background climate warming and natural variability. When a tropical cyclone encounters a marine heatwave, the interaction can be explosive. A recent paper in Science Advances documented what researchers called the synergistic impact of marine heatwaves and rapid intensification on tropical cyclone destructive power. The study, covering the Northwest Pacific and North Atlantic, found that storms encountering marine heatwaves intensify much more rapidly than those that do not, even after accounting for atmospheric conditions like wind shear and humidity. The warm ocean state can compensate for moderately unfavourable atmospheric conditions and still push storms into rapid intensification. Hurricane Michael in 2018 is one illustration. Michael intensified rapidly over the Gulf of Mexico despite relatively strong vertical wind shear. The reason was an underlying pool of anomalously high ocean heat content. Cyclone Amphan in 2020 did the same over the Bay of Bengal, strengthening even as wind shear increased, because a marine heat wave was feeding it from below. These cases break the old forecasting shorthand that says wind shear kills hurricanes. In a warming ocean, the shorthand no longer applies everywhere. Marine heat waves also widen the window during which tropical cyclones can form. Traditionally, storms needed a specific convergence of factors during a narrow seasonal peak. With warmer water lingering later into the autumn and arriving earlier in the spring, the favourable window is stretching. The 2025 Atlantic season saw much of its activity after September 10th, the climatological peak of the historical season. The 2026 Pacific season started with Typhoon Sinlaku forming in early April, rapidly intensifying into a violent typhoon. Picture a classroom with a teacher struggling to maintain order. The teacher represents the atmosphere, wind shear and dry air working to suppress troublemaking. The students are developing storms. In a cool ocean, the teacher usually wins. Students settle down. In a marine heat wave, it is as if the students have found a secret energy drink. The teacher's usual tools suddenly do not work. A mild reprimand that once calmed the class now barely registers. Storms that should have fizzled keep going. The geographic footprint of marine heat waves is also shifting. They are appearing in regions that historically experience them rarely. The Mediterranean, the North Pacific, the waters off Australia, and large stretches of the North Atlantic have all seen extended marine heat waves in recent years. Some of these regions are not classic cyclone basins, but some are. And the ones that are classic cyclone basins are seeing more frequent and longer-lasting marine heat waves overlapping with their peak storm seasons. The research implication is striking. When forecasters assess the upcoming season, they now have to consider not just average ocean temperatures, but the likelihood of persistent marine heat waves coinciding with storm development. That consideration adds uncertainty. And uncertainty in storm forecasting tends to push the tail risks upward, because the extreme events are where the marine heat wave amplification matters most, and the stakes of that amplification reach far beyond any single coast. Imagine a coast where retreat is not possible, where the next mile inland is a highway, a shopping district and 3 million people. That is most of the modern urbanized coastline on Earth. Tropical cyclones have always hit populated coasts, but the populations have changed. Over the past half-century, coastal cities around the world have expanded enormously. Tampa, Miami, Houston and Manila are just a few names on a long list of coastal metros that have tripled or quadrupled in population in recent decades. This growth matters for one simple reason. A storm's damage is a function of two things: the strength of the storm and the value of what it hits. Storms have not become dramatically more numerous. They have become somewhat stronger on average and more prone to rapid intensification. Meanwhile, the value of what they hit has exploded. Real estate, infrastructure and population density have all climbed along vulnerable coasts. The result is that even a modestly stronger storm can now produce much larger losses. A Category 4 striking near a major urban area today will do vastly more damage than the same storm would have done striking the same area in 1970. The geometry of the coast has not changed. The geometry of human settlement has. Consider Manila Bay. It is home to roughly 15 million people in the greater metropolitan area. Low-lying districts face direct exposure to storm surge. The combination of flat topography, dense development, and occasional direct hits from Western Pacific typhoons creates one of the most concentrated hurricane risk profiles anywhere in the world. Consider southern Florida. Between Miami, Fort Lauderdale, and West Palm Beach, more than 6 million people live in a narrow coastal corridor sandwiched between the Atlantic and the Everglades. Evacuation northward runs into population bottlenecks. Evacuation westward runs into sawgrass and swamp. There is no clean third option. Consider the Gulf Coast from Galveston to Mobile, a chain of cities that has been hit by major hurricanes repeatedly over the past generation. Rita, Ike, Katrina, Rita again conceptually, Michael, Harvey, Ida. Each one struck a region that, after the storm, rebuilt in place. In many cases rebuilt bigger than before. Rebuilding in place is a human choice. It is understandable. Home is home. Community is community. Economic networks are difficult to relocate. But it also means the exposure to future storms grows with each rebuild cycle. When the next rapid intensification event finds this coastline, it will encounter more buildings, more infrastructure, more people than the previous storm did. Picture a target that has grown slowly over years without the archers noticing. The archers are firing at the same spots on a map, but the target beneath is larger, richer, and more fragile than before. Fewer shots miss. This dynamic drives much of the apparent increase in hurricane damage. Climate-driven changes in storm behavior matter. Changes in exposure matter at least as much. The two effects compound. Stronger storms meeting larger, more valuable targets produce disasters of a scale that previous generations rarely imagined. The 2025 Atlantic hurricane season featured 3 Category 5 hurricanes, just one shy of the all-time record of 4. Most of the tropical activity occurred after September 10th, squeezing impacts into the late season. The 2026 season, with a developing El Niño expected to tamp down some late-season activity, still projects to bring serious threats to specific coastlines. AccuWeather's warning about potential impacts on the northern and northeastern Gulf Coast and the Carolinas is not hypothetical. It is an expectation. The infrastructure built along these coasts will be tested, and the financial system backing that infrastructure is the next piece of the puzzle. Far from the coastline in office buildings full of actuaries and risk models, a quieter storm has been building. The insurance industry has been recalculating the basic economics of coastal living. The math is not working the way it used to. Insurance is ultimately a promise. A company collects premiums from many policyholders, invests the money, and pays out claims when disasters hit. For this to work, the statistical likelihood of disasters has to be estimable, with enough accuracy to price premiums correctly. The pool of premiums has to exceed the expected payouts over time, with room for reserves. Tropical cyclone losses have been disrupting that math. In recent years, private insurers in several high-risk coastal states have reduced coverage, raised premiums sharply, or exited markets entirely. Florida and parts of the Gulf Coast have experienced some of the most dramatic shifts. State-backed insurance programs meant to be the insurer of last resort have grown into the largest providers in some regions, taking on risk that private companies will no longer touch. The reasons trace back to the underlying storm trends: rapid intensification, deeper ocean heat, stronger hurricanes, slower moving storms delivering more rainfall, and rising sea levels compounding storm surge. Each of these pressures pushes expected losses upward. Insurance models built on decades of historical climatology underestimated the present. Insurers have been adjusting. There is also a reinsurance layer that matters. Reinsurance is insurance for insurance companies, letting them spread extreme event risk globally. Reinsurers price catastrophe coverage based on their own models. When those models show rising expected losses from tropical cyclones, reinsurance costs climb. Primary insurers pass those costs to policyholders. Premiums along the coast rise. For ordinary homeowners, this shows up as higher bills, policy cancellations, or outright difficulty finding coverage. For developers, it shows up as tighter underwriting on coastal projects. For local governments, it shows up as strained budgets when state-backed insurance pools need to be replenished after a major event. Picture a seesaw. On one side, the physical risk from tropical cyclones. On the other, the financial system designed to absorb that risk. For most of the 20th century, the seesaw balanced. Losses occurred, insurers paid, and the system recovered between storms. Now the physical side is growing heavier. The financial side is scrambling to add weight. Every major storm tips the balance harder. The 2025 season, with its 3 Category 5 hurricanes, added to a multi-year trend of elevated losses. Hurricanes like Helene and Milton in 2024, together with a series of billion-dollar disasters over the past decade, have left insurers revising assumptions repeatedly. Each revision tends in the same direction. There are attempts to stabilize the system. Improved building codes in high-risk zones reduce damage from a given storm. Flood mitigation projects, better evacuation infrastructure, and coastal hardening all help. But the underlying trend in storm behavior is running partly ahead of these adaptations. For coastal residents, the practical result is a slow redrawing of the economic map. Neighbourhoods that were once insurable now are not. Properties that were once easily financed now struggle to find lenders. Property values in some at-risk zones are beginning to reflect these changes, with buyers pricing in not just current conditions but expected futures. This is not a disaster, it is a reckoning. The financial system is catching up with the physical one, and some of that catching up is reshaping where people will live in the coming decades. But before any of that, the immediate concern remains. What happens when the next rapid intensification event aims at a populated coast? The answer involves machinery most people never see. 30,000 feet above a developing hurricane, a specially equipped aircraft flies into the storm. Its wings buck through turbulence. Its radar paints the structure of the eye wall. Its crew releases small cylindrical instruments, called dropsons, into the storm below. Each dropson transmits temperature, pressure, humidity, and wind data on its descent. Numbers flow into the forecast models in near real time. These are the hurricane hunters. They are one of the most important tools forecasters have for understanding rapid intensification as it happens. In the United States, the Air Force's 53rd Weather Reconnaissance Squadron and NOAA's Aircraft Operations Center fly repeated missions into Atlantic and Pacific storms. The aircraft, including specially modified WP-3D Orions and a Gulfstream 4 jet, carry instrumentation designed specifically for tropical cyclone research. During active storms, they may fly multiple missions per day, cycling crews to keep data flowing. Dropsons measure what satellites cannot. A satellite sees the top of the clouds and infers some structure below. A dropson falls through the storm, sampling every layer of the atmosphere in a vertical column. In the eye of a major hurricane, a dropsonde can confirm the central pressure to within a few millibars, revealing the true intensity when satellite estimates may be uncertain. During Hurricane Milton in October 2024, Hurricane Hunter data showed the pressure falling rapidly. Flight-level winds reached extraordinary values. Dropsons reported pressure values near the lowest ever recorded in the Atlantic Basin. That information flowed into forecast updates hour by hour. Without those flights, forecasters would have been relying on more uncertain satellite estimates during the most critical window. International partners run similar programs. The Japan Meteorological Agency and Taiwan's Central Weather Administration support reconnaissance flights into Western Pacific storms. though at lower frequency than Atlantic operations. Hong Kong's observatory has conducted its own missions. China's meteorological service has invested in reconnaissance capacity. The quality of rapid intensification forecasts in the Western Pacific would benefit from more such flights, but logistical and political factors limit expansion. The stakes are concrete. A single Hurricane Hunter flight that confirms or refutes a rapid intensification signal can shift evacuation orders for entire coastlines. Emergency managers wait for those reports. Governors and mayors reference them. Forecasters base their public updates on them. Picture a doctor using both an external exam and an internal scan to diagnose a patient. The external exam is like satellite imagery, useful, broad, but limited in what it can see internally. The internal scan is like a Hurricane Hunter mission. Painful to perform, expensive, risky at times, but capable of revealing exactly what is happening inside. The flights are not risk-free. Hurricane Hunter aircraft have been lost in tropical cyclones over the decades, though modern safety protocols and aircraft capabilities have reduced such losses substantially. Each mission involves careful planning, with flight paths designed to sample the storm's structure while minimizing time in the most hazardous zones. New tools are entering the mix. Uncrewed aerial systems designed to fly through storm environments at lower altitudes than crewed aircraft can deliver in situ data from regions that would be too dangerous for human pilots. Small ocean drones, called sail drones, have been deployed into developing storms to measure sea surface conditions from directly beneath the cyclone. One sail drone famously survived a hurricane in 2021, transmitting stunning video and data from inside a Category 4 storm. Combine Hurricane Hunter flights, sail drones, satellites, and improving computer models, and the forecasting ecosystem is stronger than ever. But the storms are also pushing harder than ever. The contest between tools and storms is not over, and there is one region of the world where that contest runs hottest. The Indian Ocean hosts two distinct cyclone basins, the Arabian Sea to the west of India and the Bay of Bengal to the east. Historically, the Bay of Bengal has produced many of the deadliest tropical cyclones in human history, often hammering low-lying coastal Bangladesh and eastern India. The Arabian Sea, by contrast, has been comparatively quiet, until recently. In the past 2 decades, the Arabian Sea has produced a surprising number of intense cyclones. Storms like Kya, Maha, Nisarga, Tauktae, Biparjoy and others have reached severe or very severe cyclonic storm classifications, with several approaching Category 4 or 5 equivalent intensities. This represents a notable shift from the historical record. Researchers studying the Arabian Sea have pointed to warming surface and subsurface waters as a primary driver. The basin's sea surface temperatures have risen and ocean heat content at depth has increased. The atmospheric environment has also changed, in ways that sometimes favour cyclone development. Whether the change is a long-term trend or a decadal fluctuation remains debated, but the observational signal is real. The Bay of Bengal has its own story. It has always been a cyclone factory, and it remains one. But storms in this basin now routinely undergo rapid intensification, fueled by the region's persistent warmth and by the freshwater layers created by major river outflow. The Ganges, Brahmaputra and Meghna rivers deliver enormous volumes of fresh water into the bay, creating salt lids that trap heat below. Cyclone Amphan in 2020 is one example. Cyclone Tauktae in the Arabian Sea the following year is another. each strengthened in ways that overwhelmed earlier forecasting expectations for their respective basins. The human stakes around the Indian Ocean are profound. Bangladesh alone is home to more than 170 million people, many of them in low-lying delta regions directly exposed to cyclone surge. India's coasts support hundreds of millions more. Pakistan, the Arabian Peninsula states, Somalia, Madagascar and Mozambique all sit along the Indian Ocean's storm-producing margins. Cyclone Idai in 2019 struck Mozambique and Zimbabwe with devastating consequences. It was followed just weeks later by Cyclone Kenneth in the same region. The double strike overwhelmed local disaster response capacity. It also highlighted a pattern that may grow more common: intense cyclones occurring in rapid succession in the same region. Picture a forest where fires had always occurred, but usually with long gaps between them. In recent years, fires have been coming closer together. The forest has less time to regrow. Each new fire finds more vulnerable material and less recovery margin. Cyclone-prone regions are watching something similar. Each storm leaves behind damaged infrastructure, weakened coastal defences, and populations still recovering. The next storm finds softer targets. Warning systems in the Indian Ocean have improved dramatically over recent decades. The India Meteorological Department, Bangladesh's Cyclone Preparedness Programme, and partner agencies have built robust forecasting and evacuation networks. Millions of people are now moved out of danger zones before major cyclones make landfall. These efforts have dramatically reduced death tolls compared to historic disasters. But evacuation is not protection from property loss, and rapid intensification complicates even the best evacuation system. A cyclone that strengthens faster than expected can strike with more force than the evacuation plans assumed. Shelters designed for one category may face winds from a higher category. Agricultural losses, infrastructure damage, and economic disruption can exceed even the most carefully planned response. The Indian Ocean is quietly becoming one of the most important basins in the global tropical cyclone picture. And it will not be the only region rewriting its own history. Some regions of the world have, for most of recorded history, been considered essentially safe from tropical cyclones. The South Atlantic, the Mediterranean, certain high-latitude coasts in the North Pacific, the tropical Eastern Atlantic near the equator. Recent decades have begun to challenge those assumptions. In March 2004, Hurricane Katrina became the first confirmed hurricane-strength tropical cyclone to strike Brazil. The South Atlantic had never, in the modern record, produced a true hurricane. Katrina formed under unusual atmospheric conditions, strengthened, and made landfall as a hurricane-equivalent system. It caught meteorologists off guard. Since Katrina, a handful of other tropical or subtropical systems have appeared in the South Atlantic, though they remain rare. The Mediterranean has experienced its own surprises. Storms sometimes called medicanes, short for Mediterranean hurricanes, have formed repeatedly in recent decades. Most are weaker than ocean basin hurricanes, but some have reached sustained winds comparable to low-end tropical cyclones. They have struck coastlines in Italy, Greece, Malta, Libya, and other countries around the Mediterranean basin. As Mediterranean sea surface temperatures continue to rise, conditions favourable for these storms may become more common. The North Pacific has seen tropical systems pushing farther north than traditional climatology would expect. Hurricane Lane in 2018 approached close to the Hawaiian Islands with major hurricane intensity. Typhoons in the Western Pacific have, on occasion, maintained strength further north before transitioning into extratropical systems. Each of these cases is limited, None prove a sweeping trend on its own, but the accumulation of them matters. A region that hosts one unprecedented storm can be dismissed as a statistical fluke. A region that hosts several in a generation is experiencing something else. Scientists debate the exact attribution. Is it warming ocean temperatures, shifting atmospheric circulation, natural decadal variability? The likely answer is some combination of all three. What is not in dispute is that the observable map of where tropical cyclones can form is slightly different from what it was a half-century ago. Picture a painting that has hung on a wall for decades. The colours are familiar. The borders are familiar. One day, someone notices that a corner of the painting has changed shades slightly. The change is small, subtle, but real. Over the following years, more small changes accumulate. The painting is not the same painting anymore, even though it still looks mostly like itself. That is what the cyclone climatology map is doing. For policymakers and planners in fringe regions, this presents a quiet challenge. Cyclone preparedness in the South Atlantic, the Mediterranean, or unfamiliar high latitudes is typically much lower than in traditional cyclone basins. Building codes, emergency response systems, and public awareness are all calibrated to the historical threat. If the historical threat has shifted, those calibrations may no longer protect as effectively as assumed. The probability of any individual community in these regions being struck by a cyclone remains low. But probability is not the same as impossibility, and low probability events with high consequences deserve some planning attention. Some Mediterranean countries have begun updating their emergency response plans to account for Medican risks. Some South Atlantic coastal regions have added tropical cyclone watches to their weather services capabilities. These are modest adjustments. They reflect a growing awareness that the envelope of plausible weather has widened. The storms that should not have happened are the early notice that the climate system is capable of producing surprises in places we had stopped expecting them. And for the regions that have always expected them, the surprises are landing harder than ever. When a major hurricane or typhoon makes landfall, the first thing many people lose is electricity. Within minutes of the strongest gusts, trees fall onto power lines. Transformers blow, substations flood, transmission towers collapse, entire counties go dark. Restoration can take hours, days, or in the worst cases, months. The electrical grid is one of the most exposed large-scale systems in any cyclone strike zone. Overhead power lines, mounted on wooden or steel poles, are vulnerable to high winds, flying debris, and tree fall. Substations at ground level are vulnerable to storm surge. Undergrounded lines are protected from wind, but vulnerable to saltwater intrusion from flooding. Hurricane Maria in 2017 devastated Puerto Rico's power grid so severely that some communities went without reliable electricity for months. Hurricane Ian in 2022 knocked out power to more than 2 million customers in Florida at its peak. Typhoons in the Philippines, Japan, and Taiwan regularly cause multi-day outages affecting millions of people. Lost electricity is not just an inconvenience, it is a cascading public health emergency. Hospitals switch to generators, but generator fuel runs out. Refrigerated medications spoil. Home medical equipment like oxygen concentrators and dialysis machines stop working. Air conditioning fails in regions where summer heat can be lethal. Traffic signals go dark. Water treatment plants can lose pumping capacity, leading to boil water advisories. The economic toll is also severe. Businesses cannot operate. Supply chains disrupt. Cold storage facilities lose inventory. Digital commerce halts in affected regions. The longer the outage, the deeper the economic damage. Utilities have been hardening their systems. Some have aggressively buried lines in high-risk corridors. Others have replaced wooden poles with steel or concrete ones designed to withstand stronger winds. Smart grid technology can reroute power automatically around damaged sections, limiting the footprint of outages. These investments help. But the storms are also pushing against the upper end of what grids was designed to handle. Picture the electrical grid as a nervous system running through the body of a region. Every community, every hospital, every home is a nerve ending. When a storm damages the grid, it is as if the nervous system has been sliced in multiple places. Signals stop flowing. Coordination breaks down. Recovery depends on reconnecting the severed pathways one by one in difficult conditions. The logistics of restoration are enormous. Mutual aid agreements between utilities allow crews from unaffected states or countries to travel to disaster zones. Convoys of bucket trucks line up on highways for days. Staging areas cover acres. Crews work 12-hour shifts in hostile conditions, often in heat and humidity, dealing with downed wires that may or may not still be energized. Rapid intensification complicates restoration planning. A storm that was expected to strike as a Category 2 might hit as a Category 4. Utilities may have pre-staged crews and equipment based on the weaker forecast. When the stronger storm arrives, the pre-staging is insufficient. Additional resources have to be summoned from farther away, adding days to the initial response. There is also a generation mix factor. Renewable energy installations, including large solar farms and wind turbines, have grown dramatically in coastal regions. These installations are engineered to withstand hurricane winds up to certain thresholds, but a strong enough storm can damage them too. Solar panels can be ripped from their mounts. Wind turbines can be destroyed if not properly feathered during high winds. Each piece of infrastructure adds capacity but also adds exposure. The grid is a microcosm of modern coastal life, interconnected, optimized, efficient, but also fragile when major storms hit. Every improvement in one area reveals vulnerabilities in another, and the water that comes with these storms threatens systems even older than the grid. In the mountains hundreds of miles from the coast, rain falls steadily for 2 days. It is heavier than usual, much heavier. The ground, saturated from earlier rains, cannot absorb more. Water runs across the land in sheets, collecting in small streams, then larger ones, then rivers. 3 days after the storm's wind died on the coast, those rivers reach flood stage far inland. This is the inland water threat from tropical cyclones. It is one of the least publicized aspects of modern hurricanes and typhoons, and one of the deadliest. Hurricane Helene in 2024 is the defining recent example. Helene made landfall in Florida's Big Bend region. Its wind damage there was significant but relatively localized. What defined Helene's historical footprint was the water. Rainfall from the storm's remnants soaked the southern Appalachians. Rivers in western North Carolina, eastern Tennessee, and surrounding areas rose to record or near-record levels. Bridges collapsed, roads washed out, entire towns were isolated. The death toll in interior regions exceeded the death toll along the immediate coast. The mechanism is straightforward. A warmer atmosphere holds more moisture. Tropical cyclones wring that moisture out. When the storm moves inland, especially when it encounters mountains, the air is forced upward, which enhances precipitation. The result can be rainfall totals that would have been unimaginable in earlier decades. Hurricane Harvey in 2017 delivered more than 50 inches of rain in some parts of southeastern Texas. Hurricane Florence in 2018 dropped more than 30 inches in parts of North Carolina. Typhoons across Asia have produced comparable or greater totals over various regions. The list of storms that have delivered more than a year's worth of normal rainfall in a few days has grown. The consequences extend beyond the immediate flood. Saturated soils on steep slopes can trigger landslides, which are among the deadliest secondary effects of tropical cyclone rainfall. Bridges that survive the initial flood can fail during subsequent high water events when debris-laden currents undercut supports. Water supplies can be contaminated by flooded sewage systems, industrial sites, or agricultural runoff. Agricultural losses can last for a season or more. Picture rain as a deposit being made into the account of regional rivers. A moderate rain fills the river to safe levels. A heavy rain raises it to warning levels. An extreme rain pushes it past flood stage. Tropical cyclones, when they stall over one region, can deposit so much rain so fast that the rivers simply overflow their capacity to drain. Floodplains fill. Floodplains that have been developed fill with buildings. In many regions, floodplain development has grown substantially in recent decades. Communities built on what used to be recognized flood zones now face repeated inundation. Flood insurance maps, which determine where properties are considered at risk, are periodically updated, but they often lag behind the changing climate. A house built in the 1990s to code and considered safe may now sit in an area that floods more frequently than the original map suggested. The 2025 Atlantic season contributed to this pattern. The 2026 forecast warns that water threats will again be a major factor in any landfalling storm's damage profile. Forecasters increasingly emphasize rainfall and inland flooding in their communications, not just wind and surge. The old coastal mental map, where the beach gets the worst and the interior watches safely, is no longer accurate. In many cyclone strikes, the interior watches the rivers rise past their historic highs, and in the worst cases the interior loses more than the coast. The human and environmental costs of inland flooding reshape how societies think about tropical cyclone risk. Evacuation maps widen, emergency response plans extend, recovery timelines stretch, but the ocean, always, is the original source, and the ocean is doing one more thing that changes the game. Underneath every storm surge conversation sits a slow, patient number. The long-term rise in global sea level. This rise is not dramatic on any given day. It does not crash against a coastline in a single event. It arrives in fractions of an inch per year, decade after decade, invisible in the short term. But when storms hit, it is suddenly very visible. Global mean sea level has risen by roughly 8 to 9 inches since the late 19th century, according to NOAA assessments. The rate of rise has accelerated in recent decades. Projections for coming decades vary, but most major scientific bodies expect continued rise, with the range of possibilities depending on emissions pathways and ice sheet dynamics. Here is why this matters for tropical cyclones. Storm surge is measured relative to the normal sea level at the time of the storm. A surge of 15 feet in 1950 flooded areas up to 15 feet above then current sea level. The same 15-foot surge today floods areas up to 15 feet above a sea level that is already higher than it was in 1950. Every inch of background sea level rise pushes the flood footprint incrementally inland. In dense coastal development, inches can matter enormously. A neighbourhood that sat safely above historic flood levels may now sit just at the edge. A storm that would have caused moderate flooding in the 20th century can cause severe flooding today because the starting baseline is higher. sea level rise also affects the frequency of routine coastal flooding. In many cities, what used to be called sunny day flooding now occurs regularly during high tides, even without any storm. Streets in Miami, Suffolk, and other coastal communities flood during unusually high tides with no weather event at all. These are the visible early signs of a shifted baseline. For tropical cyclones, the combination of higher sea levels and potentially more intense storms compounds the storm surge threat. Hurricane storm tide, the combination of surge and tide, can reach levels that overtop seawalls and coastal barriers designed for historical conditions. Even in the absence of category-defying storms, simply hosting the same intensity storms on top of a higher ocean produces worse flooding. Picture a bathtub with a slowly rising water level. A single splash at low water might soak the tiles around the tub. The same splash at a slightly higher water level might overflow the tub entirely and soak the floor. The splash has not changed. The bathtub has. Coastal communities are the floor. Rising seas are the rising water level. Storm surges are the splashes. Coastal adaptation efforts are underway in many places. Seawalls are being raised. Levees are being reinforced. Natural buffers like wetlands and mangroves are being restored where possible, providing some storm surge dampening. Some low-lying properties are being elevated or bought out by government programs. These are real efforts. They matter. But adaptation is slow, expensive, and uneven. Not every coastline has the resources to harden infrastructure. Not every community has a political consensus on what to do. Not every developer wants to build at elevations that reduce risk but raise costs. The adaptation gap varies enormously by region and by wealth. The 2026 hurricane season, like every season before it, will feature storms making landfall on coasts that have risen relative to the storms of previous generations. The ocean has a memory, and the memory is climbing. There is one more piece to the feedback loop that ties all of this together, a loop that travels far from the storm itself into a distant region of ice and cold. Thousands of miles from the tropics, in Greenland and Antarctica, enormous quantities of ice are melting. The water from that melt flows into the ocean. Some of it stays close to the melt zones. Some of it joins the global ocean circulation and eventually redistributes around the planet. This connection between polar melt and tropical storms is subtle, but real. The most direct link is sea level rise. Ice that was previously stored on land now flows into the ocean as liquid water, raising global mean sea level. Greenland's ice sheet, along with smaller glaciers worldwide in the margins of the Antarctic ice sheet, contributes measurable volumes of water each year. The rate of contribution has increased in recent decades, particularly from Greenland and West Antarctica. As discussed in the previous chapter, sea level rise amplifies storm surge by raising the baseline from which surges are measured. Every millimetre added to global sea level eventually translates into incrementally worse coastal flooding during tropical cyclones. There's also a more subtle connection through ocean circulation. Large-scale ocean circulation patterns, including the Atlantic meridional overturning circulation, move enormous volumes of water and heat around the planet. These circulations influence where heat accumulates and where it is released. Some studies have explored whether significant changes in ocean circulation could alter tropical cyclone activity patterns, either by changing the distribution of warm water or by affecting atmospheric steering flows. These large-scale circulation effects are complex and subject to active research. Definitive conclusions about how they will specifically change tropical cyclone behavior in coming decades remain tentative, but the underlying physics guarantees that what happens in the poles and what happens in the tropics are connected, The ocean is one system. Changes in one region eventually communicate to other regions. There's also an atmospheric link. Warming in the Arctic, which is occurring faster than warming elsewhere on Earth, can alter the behaviour of the jet stream and other large-scale atmospheric patterns. Some research suggests these changes can influence the steering flows that guide tropical cyclones, potentially contributing to the slower forward speeds and more erratic tracks that have been observed in recent decades. Picture the Earth's climate system as a vast orchestra. The tropics, the mid-latitudes, and the polar regions are different sections. Each plays its own part, but each also depends on what the others are playing. When the polar section changes its rhythm, the overall music changes, even if the tropical section is trying to play its familiar part. Tropical cyclones are influenced by this interconnected music. For coastal residents, the direct consequences of polar melt are sea level rise and, indirectly, some modification of regional weather patterns. The more distant consequences, including potential changes in ocean circulation over decades to centuries, are still being mapped by scientists. What is clear is that no part of the climate system operates in isolation. The deep ocean heat feeding a Western Pacific typhoon is connected, through global currents and atmospheric teleconnections, to melting ice in Greenland, to changing sea ice in the Arctic Ocean, to shifting monsoon patterns in Asia. The storm in the photograph of a satellite image is one visible tip of a vast interconnected phenomenon. Understanding this interconnection does not provide easy forecasting tools, but it does provide context for why the tropical cyclone conversation keeps expanding. Every major storm is a local event with global context. Every adaptation effort is a local response to a planet-wide change, and the planet is not going to stop changing on the schedule that coastal communities would prefer. The question turns, finally, to what the next decades may hold. Scientists studying tropical cyclone behaviour under continued climate change have generated a wide range of projections. These projections do not predict specific storms. They describe changes in the statistical properties of tropical cyclone activity, averaged over decades. The broad consensus is as follows. The total number of tropical cyclones globally may not increase dramatically, and could potentially decrease slightly in some basins. What does increase, and this is where the concern concentrates, is the proportion of tropical cyclones that reach the highest intensities. More Category 4 and 5 storms, more extreme rainfall events, more rapid intensification events, higher storm surge due to sea level rise, slower forward speeds in some regions. These are the statistical expectations. Any individual storm in any individual year will, of course, reflect the weather conditions of that year rather than a long-term average. But over many years, the averages should shift in these directions. The worst-case scenarios are less certain and more sobering. They include possibilities like regional increases in the maximum possible intensity of storms, allowing for the appearance of storms stronger than any historically recorded. They include possibilities of cyclones forming in regions where they have historically been rare. They include possibilities of overlapping extreme events, where multiple major storms strike the same region in short succession, overwhelming response capacity. Some specific concerns have emerged in recent research. The interaction between rapid intensification and populated coastlines is one. As deep warm water pushes closer to shore, the zone where explosive strengthening can occur overlaps more directly with the zone where people live. The chance of a coastline being struck by a rapidly intensifying storm at landfall, rather than weakening as it approaches, rises. Another concern is the possibility of hurricane or typhoon behaviour that breaks current forecasting frameworks. A storm that reaches a much higher peak intensity than any in the historical record. A storm that follows a path that current models cannot reliably predict. A storm that spawns secondary hazards like tornadoes or landslides at a scale that emergency response systems cannot match. These are not predictions. They are possibilities within the envelope of what the changing climate system could produce. Some of these possibilities may never materialize. Others may become regular occurrences within decades. Picture a deck of cards where most cards are moderate storms and a few cards are catastrophic ones. In the historical deck, the catastrophic cards were rare. As climate change shuffles the deck, the proportion of catastrophic cards increases. Not every hand will contain one, but over the course of many hands, the likelihood of drawing one rises. For coastal societies, this probabilistic reality has practical implications. Planning for past storms is no longer sufficient. Planning has to consider storms stronger than what has been seen before. Infrastructure has to be designed with margins for unexpected conditions. Evacuation and emergency response systems have to be tested against scenarios that push beyond historical experience. Some regions are doing this well. Japan and Taiwan, with long traditions of cyclone preparedness, have invested significantly in infrastructure resilience and forecasting capacity. The Netherlands, though not a cyclone region, has invested for centuries in flood protection at a scale that other coastal regions could learn from. Parts of the United States have updated building codes in high-risk zones, especially after major disasters. Other regions remain underprepared. Resource limitations, political challenges, and competing priorities mean that many coastal communities face future storms with defenses designed for past conditions. The 2026 hurricane season will unfold against this backdrop. Some of it will be routine, some of it will not. The challenge for forecasters, emergency managers, and coastal residents is to prepare for both simultaneously. And one specific fear, shared quietly among those who study these storms closely, keeps returning. Ask a hurricane scientist in private what keeps them up at night, and the answers tend to converge. It is not any single element of climate change, though each one matters. It is the combination. The stacking of factors that used to be independent: deep warm water, rising sea levels, rapid intensification closer to shore, stalling storms, higher rainfall totals, salinity barriers trapping heat, expanding hotspots, denser coastal populations, aging infrastructure, insurance markets under strain, adaptation efforts lagging the pace of change. Any one of these factors is manageable. Human systems have dealt with individual stresses for generations. The specific fear is what happens when multiple factors align in a single storm event. Picture the following scenario. A tropical disturbance forms in a warm region of the ocean, over a deep hotspot with anomalously high heat content. It rapidly intensifies over unusually warm water close to a populated coastline. It is steered toward that coastline by atmospheric flows that slow its forward motion in the final hours before landfall. It arrives at a coast that has experienced background sea level rise relative to earlier decades. It delivers extreme storm surge to areas with dense development. It stalls after landfall, unloading feet of rainfall over interior regions already saturated from previous rainfall events. Its outer bands spawn tornadoes. Its wind field exceeds design specifications for local power grids. Its impacts overwhelm insurance reserves. No specific storm has combined all of these factors in a worst-case configuration. Milton came uncomfortably close on several counts. Harvey came close on the rainfall front. Helene came close on the inland waterfront. Maria came close on the infrastructure destruction front. The specific fear is the storm that combines them. It does not have to be a Category 6. It does not have to be a theoretical monster. It could be a rapidly intensifying Category 4 that hits a major metropolitan area at high tide during a peak rainfall event. That combination alone could produce consequences exceeding anything in modern history for that region. The statistical basis for this fear is not speculative. Each individual factor has been documented and attributed in varying degrees to climate change. Each trend points in a direction that raises the probability of the compound event. The timescale is the uncertain variable. It could be next year, it could be a decade from now, it could be longer, but the probability is not zero, and the probability is not decreasing. Picture a series of dice, each loaded slightly toward catastrophic outcomes. Any single roll usually produces an ordinary result. But the loading is real. Over enough rolls, the catastrophic outcomes appear more often than chance alone would suggest. Coastal societies are rolling these dice every hurricane season. The dice are being loaded by climate change, and the number of rolls is determined by the length of each season and the activity within it. The 2025 season rolled the dice many times. 3 Category 5 hurricanes emerged. The 2026 season will roll again. It may produce fewer storms, as some forecasts suggest. It may produce more, as others suggest. It will almost certainly produce at least one storm that tests some regions' preparedness. The specific fear is that eventually the dice will come up in a configuration that humans are not prepared for, not because we did not know, but because the pace of change outran the pace of adaptation. This is why forecasters who understand all of these threads are sometimes described as terrified, not by any single storm, by the trajectory of the system that produces them. But fear is not the whole story. There is also response. There is also adaptation. There is also the slow, determined work of making coastal life more resilient. Not every story about tropical cyclones is a story of rising danger. Some of it is a story of rising competence. Over the past 50 years, the death toll from tropical cyclones globally has decreased, even as the number of people living in cyclone-exposed regions has increased dramatically. This improvement is real, and it is due to human effort, better forecasting, better warning systems, better evacuation infrastructure, better building codes, better emergency response. Bangladesh provides one of the most striking examples. In 1970, Cyclone Bola killed an estimated 300,000 to 500,000 people in what was then East Pakistan. In the decades since, Bangladesh has built one of the most comprehensive cyclone preparedness programs in the world. The Cyclone Preparedness Program maintains a vast network of community volunteers, cyclone shelters, and communication systems. When Cyclone Cedar struck in 2007 and Cyclone Amphan struck in 2020, casualties were dramatically lower than historical norms for comparable storms. These were still tragedies, but they were tragedies measured in hundreds or low thousands of lives, not hundreds of thousands. The Philippines has made similar strides. The country's Project NOAA and the work of PAGASA, the National Weather Agency, have dramatically improved typhoon warnings and evacuation coordination. Japan and Taiwan have invested in infrastructure that minimizes losses from powerful storms. The United States has built the National Weather Service and National Hurricane Center into globally respected forecasting institutions. Technology has contributed enormously. Geostationary weather satellites provide near-continuous views of tropical cyclones. Polar orbiting satellites carry instruments that can measure subsurface ocean conditions. Mobile phone networks allow warnings to reach individuals in real time, even in remote regions. Social media amplifies official information quickly, though it also amplifies misinformation, a complicating factor. Building codes in high-risk regions have been revised after major storms. Homes in parts of Florida, for example, are now often built to standards designed to withstand Category 4 winds, including features like hurricane straps, reinforced roofing, and impact-resistant windows. These features cost money up front. They save much larger costs when major storms arrive. Coastal natural infrastructure is being recognized as valuable. Wetlands, mangroves, coral reefs, and oyster beds provide natural storm surge buffering. Restoration projects around the world are investing in these systems, recognizing that they provide protection more cost-effectively than some engineered alternatives. There are also emerging technologies showing promise. Artificial intelligence, as discussed earlier, is contributing to improved forecast guidance. Uncrewed aerial systems and ocean drones are gathering data from storm environments, previously too dangerous to sample directly. Advanced radar networks are providing better views of storm structure and evolution. Picture a race between two trends. On one side, the physical severity of tropical cyclones, amplified by climate change. On the other, human adaptive capacity, amplified by technology, knowledge, and organized response. The outcome of this race depends on which trend moves faster. In some regions, adaptation is winning. Bangladesh's dramatic reduction in cyclone deaths over 5 decades is one example. In other regions, adaptation is struggling to keep pace. Recent hurricane seasons in parts of the United States have shown that even a well-resourced country can be strained by rapid intensification events. The question for coming decades is whether the adaptation pace can continue accelerating fast enough to match or exceed the physical trend. The answer depends on investments, political choices, technological development, and the speed of climate mitigation. None of these factors are guaranteed. All of them are possible. There is also an individual dimension. Residents of coastal regions who take warnings seriously, who prepare their homes, who participate in evacuation plans, contribute to the overall resilience. Community-level preparation has proven, repeatedly, to be the single most important factor in determining outcomes during major storms. The quiet adaptation is not a headline. It is a daily grind of preparation, investment, and response. But it is, in aggregate, one of the most consequential human responses to any climate-related threat. And it matters because one more season is about to begin. The 2026 Atlantic hurricane season officially begins on June 1st. The 2026 Pacific typhoon season is already active, with multiple systems having formed in its first months. Other basins around the world are running their own calendars, some overlapping, some distinct. What the ocean is preparing for these seasons is a mixture of the familiar and the new. The familiar parts include the expected climatology, a Pacific in El Niño phase, which historically tends to produce certain patterns in Atlantic activity, a Western Pacific that hosts the largest share of global tropical cyclone activity, Indian Ocean basins that continue their cycles, normal year-to-year variability that will shape the specific count and intensity of storms. The new parts include the deep ocean heat reservoirs that have grown over recent decades, the expanded hotspots off the Philippines and in the Caribbean, the marine heat waves that may linger into storm season, the shifted frequency of rapid intensification, the slower forward speeds observed in some storms, the heightened rainfall potential of any landfalling system, the sea level that continues its slow climb. Forecasters heading into the season are not predicting doom. they are predicting a range of possibilities that, on average, is somewhat more severe than the historical record. AccuWeather's outlook of 11 to 16 named storms, 4 to 7 hurricanes, and 2 to 4 major hurricanes in the Atlantic is one version of that range. Other outlooks differ in details. All of them include the warning that the total count is less important than the potential for a single major storm to make a devastating landfall. The Western Pacific forecast, supported by major regional agencies, expects continued activity. Vietnamese meteorologists have publicly warned that even if total storm counts are lower than recent record years, the risk of very strong and unusual storms remains elevated due to warm sea surface temperatures. Japan, Taiwan, and the Philippines are all preparing for another intense season. For individual coastal communities, the practical meaning is clear. The coming season will feature storms. Some of them will be modest, some of them will not. The probability that any specific community will be struck by a major storm in any specific year remains low. The probability over a decade is meaningfully higher. The preparation that makes sense is long-term and habitual, not seasonal and reactive. Picture a vast ocean, warmer and deeper in heat than it was a generation ago, with currents moving energy through its depths in ways that tie one coast to another. Picture the atmosphere above it, carrying more moisture than before, with steering flows that sometimes linger over certain regions longer than they used to. Picture coastal communities, some hardening their defences, some unchanged from decades ago, all of them vulnerable in some way. This is the real setup that forecasters are looking at. Not a single storm, but the conditions that will produce whatever storms form this year and next year, and the year after that. The conditions are the story. The storms are the expression. The question that opened this whole journey was, what is behind this typhoon that has forecasters truly terrified? The answer is not a single storm. The answer is the ocean itself. Warmer than before, deeper in its heat, more persistent in its reservoirs, and closer to the coastlines that house humanity's most densely populated regions. Every storm that forms in coming seasons will draw from this ocean. Every rapid intensification event will be powered by it. Every surge will ride on top of its slowly rising surface. Every rainfall record will be fed by its moisture. The ocean is no longer the silent partner in the weather, it is the active shaper. And the conversation that follows is no longer only about the sky. It is about the water below, the water that remembers, the water that is waiting for the next storm and the one after that.